everyone, it's Dr. Greenberger here to discuss climate science. So after this video, you should be able to determine the maximum wavelength required to break a bond through photodissociation. You'll be able to think more about what types of effects different types of radiation have on gases in the atmosphere. Should be able to describe the greenhouse effect and what makes that different from global climate change. And in addition to that, be able to think about different sources and sinks of atmospheric CO2 and think about the carbon cycle some more. So let's get into it. To begin, I want to talk about water and revisit this discussion of vapor pressure. Okay, so we've seen this graph before. We're tracking how vapor pressure of different liquids changes as we increase the temperature. And so we can see that all of the liquids have this really sharp spike in their vapor pressure as temperature increases. So we have that for ethylene, for dimethyl ether, for diethyl ether, for ethanol, for water, for iodine camphor, diphenyl ether. Okay. And so we see the same kind of trend for each curve. And so we're going to discuss the origins of this shape shortly. And before we do that, I'm going to go ahead and pick out which of these liquids from the graph will have the highest intermolecular forces present. Okay, so take a second to pick out which gas you think has the highest intermolecular forces. Okay, so we know that vapor pressure is the result of molecules bouncing out of the liquid phase into the gaseous phase. And if molecules are held together more tightly, they'll be less likely to jump out and cause that vapor pressure. So we'll see that as we increase our intermolecular forces, we will decrease vapor pressure and increase boiling point. Okay. And so there's a few different ways to approach this problem. What I like to do is actually just go ahead and pick out an estimate for the different boiling points for these gases. And so if I look for the normal boiling point, which would be at 1 atm, I can just go ahead and see which one has the highest boiling point at 1 atm. And I'll find their boiling points by seeing where the curve of their vapor pressure meets my 1 atmosphere. So if I look at diphenyl ether, we'd have normal boiling occurring here, which corresponds to, over 500 Kelvin. Whereas if we look at the normal boiling point for ethylene, we see that it's more like 150 Kelvin. Okay, so diphenyl ether has the lowest vapor pressure at any given temperature. It has the highest boiling point at any given pressure, making this the molecule that has the highest IMFs. And then we would say that ethylene has the lowest IMFs. So we can make predictions about how vapor pressure of a given liquid will change as we change the temperature. And we do that using this Clausius-Clapeyron equation. Okay, so you can see we have a natural log here in the equation, and that's referring to that exponential shape that we see in our vapor pressure curves. Okay. And so we relate the two pressures at the different temperatures here. And we have to include our gas constant. And for this equation, we would use this 8.314 joules per mole Kelvin term. We want to think about increasing the kinetic energy of our liquids by adding in heat. And so we would want to keep track of joules. And then we have this delta H of vaporization. which tells us something about the intermolecular forces of a given liquid. So this equation allows us to make predictions about how the pressures change with a given temperature change. And in the Chem 110, we won't expect you to be able to plug into this. We'll let you wait until Chem 112 to actually use this equation mathematically. Okay. And it is a form of what we call the Arrhenius equation, which is one of the most important equations that we see kind of throughout all of science, really trying to understand what makes different processes happen from an energetic standpoint. Okay. So if we think specifically about water in this equation, we know that more water will be in the atmosphere as more heat is added into the atmosphere. But then we also know that water is a greenhouse gas. And so what ends up happening is if we heat up the earth, we get more water in the atmosphere, which means that we get more heat, higher temperature, which means we get more water dissolved in the atmosphere, and this goes on and on and on. And so when you have two different effects that kind of feed into each other and cause the other to keep happening, we call that a positive feedback loop. Ooh. Okay. Sorry, disregard the wild pen there for a second, but we'll call this a positive feedback loop. Okay. And we can look at the data that supports this idea here on the next slide. So what we have are two curves showing us the vapor pressure of water as temperature changed. And these were both modeled using the Clausius-Clapeyron equation. So if we look at this graph on the right, we have a much broader temperature scale. We go all the way from 0 to 120 degrees Celsius. And we can see that full increase of water's vapor pressure as we increase temperature. But if we want to think about what goes on in the atmosphere, we're going to look more at the temperature regions in this red box rather than the full blue curve. And so if we zoom in to that temperature region here on the left, it looks fairly linear. We're just really zoomed into this curve. But we can compare our current temperature, the average temperature on Earth, which is about 14.6 degrees Celsius, to what the temperature is if we add 1.5 degrees Celsius, which gives us, a little above 16 degrees Celsius. We can see that the vapor pressure changes from about 15.4 to 16.9 torr. And when we look at the percent change, this corresponds to a 9.3% increase. So changing the ambient temperature by just 1.5 degrees Celsius results in about a 10% increase in that humidity, in the vapor pressure of water, which will then encourage more of a temperature change, which will then encourage more water to be dissolved. Okay. And so we can kind of look at the type of radiation that water absorbs here on this plot. Okay, so we talked about that positive feedback loop and how water can store energy. And so what we have here in this graph, and we'll continue talking about it on later slides, is the amount of infrared radiation that reaches the Earth's surface marked in green, as compared to the red area, which is the infrared radiation that is able to bounce off of our planet and reach back out to outer space. And so really where you're seeing the green is telling us about radiation that gets absorbed by the Earth. And the red is showing us what's able to escape. Okay. But when I say by the Earth, I mean by the Earth and its atmosphere. And so we can see that water is able to absorb a pretty broad range of infrared light. Okay. And so by absorbing that infrared light, water's contributing a positive term to the delta E, like the internal energy of the planet. And changing the internal energy of the planet and changing the humidity level of the planet has really intense consequences on extreme weather events. And so I'm sure we all remember from just very, very recently, Hurricane Harvey and Maria. These were two really devastating storms that affected Texas, Puerto Rico, the Dominican Republic, and other islands and countries in that region. And each one of these were referred to as 500-year storms, which means that a storm of that magnitude, so one storm, should only occur every 500 years. Meaning that there's a 0.2% probability of a storm occurring with that strength in a given year. And what we saw happen was that we had two of those storms in the same year, which has a 0.0004% probability of happening. So changing the amount of energy stored in the planet and the amount of water available in the atmosphere can really change how our weather patterns behave. Okay. And so on the previous slide, we talked a little bit about infrared light and how it increases the kinetic energy of molecules, oftentimes by adding vibrational modes to different molecules and how they move around. But we can also think about how high energy light is capable of breaking bonds. And so what I have written here is the idea that a carbon-nitrogen bond has a bond dissociation energy, or bond enthalpy, of 770 kilojoules per mole. So that's how much energy it would take to break 1 mole of bonds, so that big group of bonds. And what we're trying to figure out then is what wavelength of light would have enough energy capable of doing that breaking. So I'm going to start solving this by saying I don't want to think about a mole of photons when I'm doing wavelength. I want to think about just one single photon. So I'm going to convert the 770 kilojoules per mole of bonds to saying for every 1 mole of bonds, I'm going to have Avogadro's number of bonds. And then just to get my units into units we're used to thinking about for light, I'm going to also say that I'll have 1,000 joules for every 1 kilojoule. And I'll see that this ends up being 1.28 times 10 to the negative 18 joules would be required to break 1 bond. And so I want to think about just for 1 photon breaking 1 bond. So I can go ahead and use this value as my energy, E, and set up an E equals HC over lambda equation to relate energy and wavelength. So I'll have my energy, which will correspond to just the energy in one photon to break one bond. I'm going to go ahead and write this as joules per photon. This will be equal to Planck's constant, times the speed of light divided by wavelength, which is what we're solving for. And so when I go ahead and do this computation, multiply over by wavelength, divide by my energy, I'll find that lambda pops out as 1.55 times 10 to the negative 7th meters, which is going to be the same as 155 nanometers. Okay, and so this would be our maximum wavelength capable of breaking that bond. And any wavelength with a shorter, or any photon with a shorter wavelength than that would also be capable of breaking that bond, because it would reach the maximum amount of energy required to break it, and even have more energy then. And this photon is, of course, in the UV region. And so we want to think about how different photons interact with different gases in the atmosphere. And so as we saw this plot previously, we can see that the highest energy light is absorbed in the thermosphere. And we see these ionization reactions, which result in just free electrons in the atmosphere. So it's a very high energy process. And we get some of that happening in the mesosphere, but then here in the stratosphere where the UV light is absorbed, we would start to see the photodissociation as we calculated on the previous slide, where we start to break bonds. Okay. And then here, visible light contributes to these electronic excitations, and then IR light contributes to vibrational modes and having molecules bend differently along their bonds. Okay, and so we talked a little bit about this plot previously. We said that this green region corresponds to the amount of radiation in the infrared region that's at the Earth's surface. And then the red is what's capable of leaving and passing through our atmosphere. And so the green that's shown beneath the red is what is absorbed by the atmosphere. And the gases that are contributing to that absorption are what we call the greenhouse gases. And we can see some of those listed here. We have CO2 absorbing in 2 different regions. We have water absorbing in 2 different regions. We have methane and ozone absorbing. Okay. And so it's their absorption that contributes to the increase in the kinetic energy of the Earth and an increase then in the Earth's ambient temperature. And so we can talk about what causes a molecule to be capable of absorbing IR light. And we say that it depends on asymmetric bonds. And we also say that this is if we have any polar bonds. Usually those will show up as infrared absorbing. And so in this graph down here shown at the bottom, we see that any dips correspond to absorption of infrared light. And different functional groups will absorb different types of infrared light. And we'll say that most of the gases that we look at in Chem 110 absorb IR light unless they are the diatomic gases, because those will be completely symmetric molecules. The noble gases also do not absorb infrared because they're just single atoms. There's no kind of asymmetry to them. Okay. So generally we'll say polar bonds contribute to molecules' electronic asymmetry, which is the asymmetry of bonds, which is what infrared then will probe. And so we know that if we look up at the sky every day, it looks a little different, right? Some days we have lots of clouds, some days we have no clouds. Most days here in State College, we have lots of clouds. Okay. But those different changes in what's present above us will change how the light is reflected or absorbed by the Earth and its atmosphere. And so, of course, here in the center of our diagram, we have the sun. Wearing his sunglasses. Okay. And what we'll see is that most UV and visible light passes through the atmosphere. And the infrared is largely retained. And the retention of that infrared light is what we call the greenhouse effect. And so we can look at how the atmosphere, does reflect some light, not a ton, 6%. Clouds reflect about 1/5 of the light that comes in. The Earth's surface reflects some. But the Earth's surface absorbs about 1/2 of the light that reaches it. And some light bounces off. And then maybe it's absorbed by water in the atmosphere via the greenhouse effect, or radiates out into space. Okay, so there's lots of different processes that contribute to light coming in and exiting then the atmosphere. And most of the infrared light is absorbed by gases in the troposphere, which is, of course, the layer of the atmosphere where we live. Okay. And so we do say that water is one of the most potent greenhouse gases. And, this does work in our favor to a certain extent because water and CO2 and other greenhouse gases are what maintain a temperature at the Earth's surface that isn't too cold. When there's none of these gases present in the atmosphere, that's when we get our frozen ice planet. And so we're kind of trying to maintain a balance where we're not frozen, but we're also not too hot. Okay. And so this is getting back to that idea of greenhouse gases and infrared gases, and it's showing some of gases that infrared light is absorbed by. And we can see here some of the different stretches or bends we call, or vibrations, just different way that molecules can move as they absorb infrared light. And so we've talked about kind of how we have our molecular dance party. So our symmetric stretch is when they would go in sync with each other. Asymmetric would be when they go out of sync with each other. And you have bending, you have rocking, all kinds of dance moves. Okay, and so as we mentioned, our diatomic gases, like N2 and O2, are not greenhouse gases, though they do compose about 99% of our atmosphere. But then here we have a bunch of different gases that have asymmetric bonds. Okay. They have different bond dipoles, and therefore will absorb IR and be greenhouse gases. And you can play with these stretches in the ebook. It's pretty fun. Excuse me. Especially if you make them the space filling model, it can be pretty silly. Okay, so check that out. Okay. And so we've been referring a lot to how increasing the Earth's internal energy will correspond to an increase in temperature. And this graph is kind of showing us that change. So to understand this graph, we just want to look kind of in this box here marked as the baseline years. So what they did here was say this time period we're going to call 0. And so then, since kind of these years were colder, they're going to have a negative value. And then if the temperature ever is greater than it was during this time period, we have a positive value. Okay. And so then what we see is that before this time period, in the early 1900s and such, we were a little colder, and there's definitely some oscillation, but pretty steady temperature changes. But then when we look on the other side of this time period, now we have a very, very, very steep increase in our temperature that's never really coming back down. And then this can kind of be a problem when we think back to vapor pressure and water, because we know that then as we increase our temperature, we're going to increase the amount of water in the atmosphere, which will then increase our temperature. Okay, so we get our positive feedback loop. And so the goal of current efforts is to try to taper this curve so that our increase is not continuing at such a steep rate. So we can see that that temperature has increased about 1 degree Celsius. And what we see also happening at the same time is that the amount of atmospheric CO2 is increasing. And so we've gone from, the 60s and before, when we were about 300-ish ppm of CO2. Then over time to now, we see that we've surpassed 400 ppm CO2. And so we're seeing that even as the temperature increases, CO2 concentration also happens to be increasing. And we also know from our understanding of absorbing IR in polar bonds and asymmetric molecules that CO2 is capable of absorbing infrared light and increasing the kinetic energy of our atmosphere and increasing the temperature then. And so when you look at this graph, you can see it's really squiggly on like the short time period. And all that's showing you is the oscillation between when there's leaves on the trees versus not leaves on the trees. Okay. So we see the seasonal oscillations in red. Okay. And then on the right, we have this graph that tells us about the concentration of CO2 from thousands and thousands of years ago. And so what they do is they go up to Greenland or somewhere with really deep ice and glaciers, and they core through the glaciers. So they just kind of get like a big piece of ice going back in depth, which is like going back in time. And they look at the amount of dissolved CO2 in the frozen water. And so, about 40,000 years ago, it was about 200 ppm. And, there was a spike, 20, 15,000 years ago increase. But then if we look starting about here, suddenly there is this really uncharacteristic spike in the CO2. That's way steeper than any previous sort of pattern we've seen. Okay. And so to understand this spike, we have to understand how carbon is stored and translated between different storages of that carbon in the carbon cycle. Okay, so before we get into that, let's think about this car emitting CO2. So go ahead and take a minute and see if you can figure out what volume of gas would correspond to 4.6 kilograms of CO2 at standard temperature and pressure. Okay, if you haven't finished yet, go ahead and pause, keep working, that's great. I'm gonna go ahead and go through the question now. So we know that we can relate moles of a given gas to volume through PV equals nRT, one of our new favorite equations. And in order to do that, we need to convert the grams of CO2 into moles rather than grams. And so we get this 4,600 grams of CO2 by just saying 4.6 kilograms is equal to 1,000 grams and 1 kilogram. And then we have the molecular weight of CO2 from the periodic table here, giving us 104.5 moles of CO2 released by the average car every year. And then we can use PV equals nRT to solve for the volume. And part of that requires recognizing that STP will correspond to 1 atm pressure and 273 Kelvin, or 0 degrees Celsius. And then when we solve for volume, find that it's about 2,340 liters of CO2. Okay, so it's a pretty big volume of CO2 given off by every car. And there are a lot of cars out in the world. Okay. So now we can talk about the different carbon reservoirs. So I'd actually like to start by talking about the bottom part of this diagram, where we have our long-term reservoirs. So we have sedimentary rock, very deep. Then we have, the rock that's at the bottom of the ocean, and fossil fuels that are, have to be mined out of the earth. So these are our long-term reservoirs. And so the oceans do kind of contribute to pack some gigatons of carbon every year and move them into the long-term reservoir, okay, as shown by this green arrow. You can see that's only 2 gigatons per year, okay, compared to all the other changes that are happening up above. And so we can see that moving between the different short-term reservoirs, like from the ocean to the atmosphere, from plants and soil to the atmosphere, happen in all kinds of different ways. So the ocean gives off a certain amount of CO2, but it also takes up a certain amount of CO2. And then we see that as plants and such decay, they give off some CO2, but photosynthesis retraps that. And what we start to see is on the right here with these goldish brown arrows, we have the effects that are caused by humans. Okay, so these arrows are caused by our actions directly. So we can see that deforestation leads to more CO2 ending up in the atmosphere. Combustion, so this is like cars, factories, coal, results in 8.4 gigatons per year carbon going into the atmosphere. And then producing cement actually requires taking limestone and turning it into cement, which releases CO2. And that also contributes to putting more CO2 in the atmosphere. Okay. So even though most of the carbon is in these long-term reservoirs, we are removing it from the long-term reservoirs and moving it into these shorter-term reservoirs. And so when we talk about this, the carbon cycle, we're oftentimes discussing sources and sinks. And so source is, as it sounds, the source of which something ends up, the source of the gas that ends up in the atmosphere. And then the sink is a way, it's more like sinking in the ocean rather than like kitchen sink. But it's the way by which a gas can be removed from the atmosphere. So some sources for adding CO2 into the atmosphere include decaying matter, oceans releasing dissolved CO2, respiration of animals like us. Volcanoes can release some CO2. And then here we have our what we'll call anthropomorphic or human-caused sources of CO2, like combustion of fuels, deforestation, and manufacturing cement. And so then some natural sinks for CO2 include forming new rocks, dissolving CO2 in the ocean, and then photosynthesis where plants trap it into sugar. So we can say, is this change in CO2 really due to anthropomorphic sources? And so what we've done here is kind of counted up all the different numbers in the different arrows. And so we can see that each year, 210 gigatons of CO2 are removed from the atmosphere every year, mostly from photosynthesis in the oceans. But then we can see that 220 gigatons of CO2 are released into the atmosphere every year. So we have these man-made sources of CO2 that contribute 10 gigatons of carbon dioxide into the atmosphere every year. And so it's this change that is increasing the amount of infrared light that's absorbed by the atmosphere, which increases the energy stored in our planet and increases then our average global temperature. Okay. With that, I'll let you all go. Have a great day.